So before we look at limits, we want to just review reading graphs in general because this is a very important skill. Typically, we're going to be studying graphs in 2 dimensions, so we're just going to have 2 main components. The 2 main components of graphs are going to be inputs and outputs. Now these will be represented by variables or some type of letter, but if you don't see those letters introduced, we can fall back on the conventional variable choices, which are x and y. It won't always be x and y, but of course these are the common ones so that everyone's sort of on the same page if it wasn't explicitly stated. The input values are usually found along the horizontal axis, so this is the input axis, and the output values are usually along the vertical. So when we're analyzing graphs, which maybe we have a function that looks like this, and let's call that y equals f of x. Now, if I'm going to analyze this graph, this function, I might talk about the behavior of the graph. The behavior has to do with the output values. When that behavior occurs has to do with the input values. So the word when is commonly used for describing input location, while the word what is commonly used to describe output location. A word that is used to describe either of these is where. Usually you might see it used for input values more. At least I know that I use where when talking about input values more often than when I'm talking about output values. But we're going to see in this next lesson that we might use where for either one. And that's because the graph, right, both the input and the output axes are locations. And so where is a way we talk about location. So you will notice it both, and that's why using the word what or when might help us distinguish between the two. Now let's look at an example here. We have a function named h, and I might ask, what is h of 1? Now my knowledge of function notation should tell me that this is an output, right? I can tell just by looking at it, and they told me my input is 1. But this word what is an example of a clue, right? The way we talk about outputs, as soon as I see the word what, I know I'm looking for an output. And so I just need to read this graph. Well, here's the input, x equals 1, right? And I can just look on this graph and see that there's a point right here, and therefore the output is 5. But I could have asked this question a different way. I could have said, when is h of x equal to 5? And now, again, using function notation, I know that they've given me the output. Okay, this is my output. And I need to find the input, but that word when confirms my thoughts, right? When is how we talk about input values. And so I would just be reading this graph backwards and say, okay, they gave me the output of 5, and that only happens when x equals 1. Well, actually, it doesn't. This one's more interesting because this one happens again when x equals 5, and again when x equals -1. So that was actually not the only time, right, that the output is 5. When we look across the whole way, we see that there's multiple options here. But I might want to ask more interesting questions if I'm trying to analyze this. So what if instead of asking what is h of whatever, or when is h equal to whatever, I might say, what happens as x gets closer to 1? And if I look at the graph, I know now that I'm still looking around when x is 1, but I'm not told that I'm actually on that value. I'm getting close to it. So let's just first find where it's 1. So I'm looking somewhere here on the graph. But I want to get closer to 1 and not actually just jump straight to it, right? I want to arrive there. I want to journey there. And so the way I might do that, right, is following this path, and I could follow it from the right or the left. In either case, I see that I'm approaching the same location, right? As I get close to 1 from the left, or as I get close to 1 from the right, it looks like they're both going towards the output of 5. So I could say h of x gets closer to 5. Let's try another one. What if I asked, what happens as x gets closer to 4? So we want to first find where we're looking. So around here, right? Kind of zoom in a mini neighborhood. And we can see that there's actually a hole at 4. The actual output is over here. But again, we're not trying to jump straight to 4. We're trying to approach it and journey there. Imagine if you're driving a car, right? So what I want to do is let's just remove this for just a second. So if I said we were trying to get closer to 4, as x gets closer to 4, which is somewhere here, I can see the only ways to get there are if I come on this road from the left or on this road from the right. And again, they look like they're going towards the same place, which is maybe here-ish, right? Just put like a little star. And that looks like the output, I don't know, 4.5, 4.6-ish. So we're thinking h of x gets closer to 4.6 about. If we go back to the original picture before I removed anything, I can see that that's indeed where the hole looks like it is, right? Around 4.6-ish. But that means that the function never gets there, right? There's a hole. I'm trying to drive somewhere and it's like it was removed from the ground. But that's okay. That wasn't what the question was. I didn't say, what is h of 4? I said, what happens as x gets closer to 4, right? And that's what it looks like it's doing. It's h of x is getting closer to 4.6. So even though there's a hole in the graph, I can still answer this question. H of 4 is a completely different number. The answer is 4, right? But that's not where the roads were leading to. There's actually no roads around this point. And so that's not how we would answer this question. I do want to point out that if you look at the last question, right, it looks like they're getting to 5 and we actually have a point at 1, 5. Sometimes you can get there, sometimes you will not. That's totally fine. The point of it is not whether or not you arrive, it's what is the destination. Let's look at a trickier one. What if we looked at what happened as x gets closer to -1? So again, we want to locate where that is. So -1 is here, right, along this line. And if we tried to get closer to this area, not seeing the end result, we'd be trying to approach from the roads to the right and to the left, right? So here's from the right, here's from the left, right? And so if we put the picture back in, we can see, oh, this road is leading towards 5, and this road is leading towards 4. And so now they're not headed towards a common place like the other two examples. The other two examples, I could give one answer. But in this case, now it kind of depends on which direction you're heading from, right? If you're coming from the right, well, I can answer you, it's 5. But if you're asking from the left, then I have to change my answer. And so this is another important idea. We can see that in this case, we have two answers that are different from each other. We don't have a common destination. So what is a limit? A limit is the destination. Again, we do not necessarily care if we arrive at the destination. We're just wondering where the roads are pointing to. Now we saw that that might depend on if we're coming from the left or from the right. So this is what we call one-sided limits, left-sided or right-sided. Now, if it is not specified that we're looking just from the left or just from the right, we want to assume we're looking from both. And the only way that a limit is going to make sense is if both of those roads go to the same place. We need a common destination. Basically, the roads should be connected. Now we're going to look at notation for this right now so that we can start communicating this in math versus just saying, where does it look like H is going to as X gets closer to whatever, right? That was a lot longer, long-winded, wordier. We want to cut that down. So a limit will be denoted LIM. And so to locate the input, we're going to give the little when X gets closer to whatever number you want. So A is a placeholder, right? Limit as X approaches the arrow, right? Gets closer to A. What are we observing, right? The function itself. So f of x goes here. This is how we write limits. This is how we ask what happens to f as x gets closer to a. right? Limit of f as x approaches a. Now, if that limit exists, we set it equal to whatever that number is, right? We say the limit is L. One-sided limits are going to look exactly the same. So limit of f of x as x approaches a. But if we're coming from just the left side, we're going to put a little minus there to show it's from the left of a. So I'm sure you can guess that the right-sided limit would be as x approaches a with a little plus. Now, when we say the limit only exists if the one-sided limits are consistent, are the same, that means we're looking to see if these are equal. If they are equal, then the limit, the total limit, right, from the left and the right exists. And that's pretty much it. That's just a basic introduction to limits, this idea that it's the destination, and we want to keep that in mind because it'll help us figure out how to find limits from graphs. So until next time, bye.